In this video, we want to look at the patterns that result when we take a binomial, a plus b, and raise it to a power. Power 2, power 3, power 4, power 6. What do I get when I expand this binomial out? Alright, so let's start with something we're familiar with. A plus b squared. We've multiplied this out many times, and we know that that's going to result in this. So now let's look at a plus b cubed, which we know would be a plus b times a plus b times a plus b. And so to multiply that out, we need to multiply two of them together at a time. So we know that's a squared plus 2ab plus b squared, and we need to multiply this by a plus b to get it all expanded out. And so I can take that term and multiply to each one here, which is going to be a squared times a plus b plus 2ab times a plus b squared times a plus b. And then I can distribute that out. And now I'm going to collect like terms. And so I have a cubed. I have two terms that are like here. That would be 3a squared b. And I have two like terms here, which would be 3ab squared. And I have that one on its own. And so I have four terms in the expansion of a plus b cubed. I had three terms in the expansion of a plus b squared. And so if I now wanted to go and expand a plus b to the fourth, I would expect there would be five terms. Now, if I want to expand out a plus b to the fourth, I'm going to need to take my previous answer and multiply by another a plus b, and you can do that on your own and figure that out, or you can just believe me that it would turn out to be this. Alright, and so with the power of 4, we get 5 terms in the expansion as expected. Now, the question is, do I notice any patterns in these expansions of the ones I've done, a plus b to the second, to the third, to the fourth? Do I notice any patterns in the terms that would allow me to do higher power exponents without having to multiply by hand step by step the way I was doing here? Well, the first thing you'll notice, I hope, is that when we have a plus b to the fourth, the powers of a start with the exponent on the binomial 4 and decrease term by term as we go down the line. A to the fourth, a to the third, a to the second, a to the first, and the last term can be thought of as having an a to the 0, because that's 1. The powers for the second term in the binomial, b, do the opposite. They increase term by term from power 0, because b to the 0 is 1, b to the 1, b to the 2, b to the 3, b to the 4. Alright? What about the coefficients? For a plus b to the fourth, I have coefficients of 1, 4, 6, 4, and 1. For a plus b cubed, I had coefficients of 1, 3, 3, 1. A plus b squared, I had coefficients of 1, 2, and 1. And perhaps those numbers are, hopefully those numbers are familiar to you. In fact, they are the numbers in Pascal's triangle. For row 3, the numbers 1, 2, and 1 correspond to the coefficients in a plus b squared. This was when n was 2, in a plus b to the n. These are the coefficients in a plus b to the third. The coefficients in a plus b to the fourth. And so you would expect, and in fact it's true, that the coefficients for higher powers are numbers found in Pascal's triangle, which, remember, the numbers in Pascal's triangle represented choose values. So when I get down to n equals 6, the value of this is 6 choose 0, 6 choose 1, 6 choose 2, etc. So all of these patterns that we've discussed in the expansion of a binomial are represented in what we call the binomial theorem. A plus b to the n expands out into n plus 1 terms. And the terms in the expansion have three major things happening. First of all, the powers of a start in the first term with a to the n and drop as we go from term to term, a to the n minus 1, a to the n minus 2, down to a to the 0. The second thing is that our powers of b start with exponent of 0, b to the 0, and increase b to the 1, b to the 2, b to the k, up to b to the n in the last term. And the last thing is that the coefficients of our terms are the n choose values, starting at n choose 0 in the first term, n choose 1 in the second term, n choose 2 in the third term, n choose k in the k plus first term, and n choose n in the n plus first term. Notice that in our general term, where we have n choose k, the exponent on the b matches the value of k, and the exponent on the a is n minus k. The exponents of the a and the b always have to add up to what n is. So if our exponent on b is k, then our exponent on a must be what's left over, n minus k. And so our representation of a general term, the k plus first term, is n choose k, a to the n minus k, b to the k. So let's use the patterns that we've discovered, represented in the binomial theorem, to expand a plus b to the fifth, which, because the exponent is 5, the expansion will have 6 terms in it. And so our terms will be something a to the 5, b to the 0. Powers of a will drop by 1. Powers of b will increase by 1. I'm just leaving the coefficients till the end, so I'm just putting a blank for them for now. And then I know my coefficients are going to be the 5 choose values, choose 0, 5 choose 1, and so on. And I can look these values up in the 6th row of Pascal's triangle. And so this is going to reduce 5 choose 0 will be 1, a to the 5th, b to the 0 is just 1. 5 choose 1 is 5 from Pascal's triangle. 5 choose 2 from Pascal's triangle is 10. 5 choose 3 is 10. 5 choose 4 is 5. And 5 choose 5 is 1. So it's 1 b to the 5th, and I have my 6 terms in the expansion of a plus b to the 5th. Here's a situation that's a little more complex. My a value is 2x and my b value is negative 3. And so my expansion is going to be something 2x to the 4th, b to the 0. Next term, the powers of 2x are decreasing, powers of negative 3 are increasing. and then our blanks will be the 4 chooses. 4 choose 0, 4 choose 1, 4 choose 2. And I'm just going to take those from Pascal's triangle. Those values will be 1, 4, 6, 4, and 1. But those numbers are going to look different in terms of coefficients because we have other things happening with our a and b, numbers that are being affected by the exponents. So we need to simplify this carefully. We're going to have 1. We need to work out the exponent. 2x to the 4th is 16x to the 4th. Negative 3 to the 0 is 1. Then we're going to have 4, 8x cubed times negative 3 plus 6, 4x squared times 9 plus 4 times 2x times negative 27, which is what that is, plus 1, there's 1 there, and negative 3 to the 4th will be positive 81. So simplifying, we're going to get 16x to the 4th. Multiplying this, we'll have a negative 32 times 3, 96x cubed. 24 times 9, that's 216x squared. Our next term will have a negative in front. 8 times 27, that's also 216x. And this is plus 81. And there's our expansion. You'll notice that the terms alternate in sign, positive, negative, which is always what happens when you have a negative in the middle of your binomial. Finally, sometimes you're just asked for a particular term in the expansion. So if we wanted to know the 4th term in the expansion of this binomial, we know the fact that we have a 9 up here means that the expansion has 10 terms. And we know that our formula for the k plus first term is n choose k, a to the n minus k, b to the k. I just remember this by these two match, and then this exponent is n minus this exponent. So there's my formula. Now we want the 4th term, and if we want this to be the 4th term, that therefore means that we're talking about k being 3. And so we can substitute our values. Our n value is 9. And so we want 9 choose 3. This will be 3 and this will be 6 because these have to add up to whatever n is. 9. These match, remember? So this is 9 minus 3, 6. Be clear in your mind as to how you're calculating those. And then your a value is x, and your b value is negative 3. So if we work all this out, 9 choose 3, I can get that from the calculator or Pascal's triangle. That's 84, x to the 6th, and this is negative 27. And if you combine that, your 4th term will be this.